Good day, everyone. We are pleased to present our undergraduate thesis titled Enhanced Heterogeneous Photophantom Degradation of Aniline Using Fe3O4 at CSBC Catalyst, which is magnetite supported on coconut shell biochar. I am Johanna Jiril V. Calbe, and joining me is my research partner, Elvin Melenci Alcabaza. Together, we'll be discussing the effectiveness of the Fe3O4 at CSBC catalyst in degrading aniline in wastewater through the photophantom process, and how each parameter, solution pH, hydrogen peroxide concentration, and catalyst dosage impacts the degradation efficiency.
Hi, I'm Melvin. What is aniline? Also known as aminobenzene or phenylamine, it is used extensively in the production of various consumer and industrial materials. It serves as an essential intermediate in the synthesis of dyes, pharmaceuticals, and agricultural products. However, aniline poses significant hazards due to its high toxicity and stability. It is recognized for its potential mutagenic and carcinogenic effects. It is often released into the environment through industrial wastewater, thereby posing considerable risks to aquatic ecosystems and human health. Ongoing research focused on developing efficient and sustainable methods for degrading aniline in contaminated water. Techniques such as biological treatment, membrane separation, thermal oxidation, and adsorption were explored but faced limitations including slow degradation, membrane fouling, secondary pollution, and poor performance. Advanced oxidation processes, or AOPs, particularly phenton-based reactions, showed promise as environmentally friendly methods for effectively degrading resistant pollutants like aniline. The improper disposal of aniline continues to pose serious health and environmental risks. To address these concerns, the study aligned with key sustainable development goals such as SDG number 3, good health and well-being, by reducing health risks associated with chemical exposure. SDG 6, clean water and sanitation, by preventing water contamination. Since completely avoiding aniline is not feasible, it is crucial to degrade it into less harmful forms before release. This research served as a vital step towards minimizing environmental impact through effective degradation and safer industrial disposal methods. The coconut shell is sourced locally and turned into biochar using a tube furnace. By varying parameters such as pH, hydrogen peroxide concentration, and catalyst dosage, the degradation process was evaluated under different conditions. The initial and final concentration of aniline was measured using UV-vis spectroscopy. In the process, an aniline solution was treated with a catalyst and hydrogen peroxide under UVC light. The treatment lasted 30 minutes to determine the efficiency. Response surface methodology with a box Benken design was employed to evaluate the impact of the parameters on aniline degradation. RSM assisted in modeling and optimizing these processes. 27 runs were conducted to find the optimal conditions for maximum degradation efficiency and to analyze the significant effects.
Next is the presentation of the results and discussion together with the statistical analysis used in the study. Let's start with the individual degradation contributions of each component in our system. We ran a series of tests using different combinations of UVC light, hydrogen peroxide, and the Fe3O4 at CSBC catalyst to see how each one performs, alone and together. From the table here, it's clear that UVC light alone and hydrogen peroxide alone resulted in almost no degradation. When we combine UV with either the catalyst or hydrogen peroxide, performance slightly improved to around 1 to 4% aniline degradation. But once all three were combined, light, hydrogen peroxide, and catalyst, we achieved a 33.6% degradation, proving that the process works best as a complete system. This confirms the synergy required for effective hydroxyl radical generation and pollutant degradation. Next, we ran 27 experiments using different combinations of pH, hydrogen peroxide concentration, and catalyst dosage. As discussed earlier, the values were selected based on optimal ranges from similar studies. To isolate the effect of each parameter, We average degradation values across each level while holding the others constant. In the first figure, we can see that the degradation increases as pH rises from 2.1 to 4.50. The highest degradation was observed at pH 4.50 with an average of 32.4%. This aligns with other studies suggesting that heterogeneous photophantom systems perform better near neutral pH due to improved catalyst stability and better aniline adsorption. In figure 2, degradation peaked at 150 mg per liter of hydrogen peroxide with an average efficiency of 27.6%. However, when we increase it to 300 mg per liter, degradation dropped. This is due to radical scavenging where excess hydrogen peroxide reacts with hydroxyl radicals, reducing their availability for degrading pollutants. In figure 3, increasing the amount of catalyst resulted in a steady rise in degradation from around 10% at 1 gram per liter to 33% at 4.2 gram per liter. This is likely due to more available active sites from the Fe3O4 at CSBC catalyst, supported by the high surface area of coconut shell biochar. It's worth noting that too much catalyst can lead to light scattering or particle agglomeration, but 4.2 gram per liter remained within the optimal range in our setup. The figures give us a preliminary understanding of how each parameter affected degradation, but to further model their relationships, we used response surface methodology with the box Benken design. We started by comparing different model types: linear, two-factor interaction, quadratic, and cubic. From the model fit comparison, only the linear model showed a p-value less than 0.05, specifically 0.0009. This means a simple linear relationship was sufficient to explain how the parameters affected degradation efficiency, and more complex models were unnecessary. Next, we performed analysis of variance on the linear model. The analysis showed that the catalyst dosage had the strongest effect on aniline degradation with a p-value of 0.0015. This was followed by pH which had a p-value of 0.038. Both were statistically significant. In contrast, hydrogen peroxide concentration was found to be not significant with a p-value of 0.6504. This suggests that within the range we tested, hydrogen peroxide didn't have a strong influence on the degradation process. The ANOVA findings were further supported by the regression coefficients. Both pH and catalyst dosage had positive coefficients, meaning that as their values increased, degradation efficiency also increased. On the other hand, hydrogen peroxide concentration had a negative coefficient of negative 1.36, indicating that higher concentrations may slightly reduce efficiency. This again points to the scavenging effect of excess hydrogen peroxide, which interferes with the availability of hydroxyl radicals. The perturbation plot illustrates how sensitive aniline degradation efficiency is to each individual factor, while the other variables are held constant at the midpoint. The steepness of each line reflects the relative influence of that factor. Catalyst dosage had the steepest slope, showing the most significant effect on degradation efficiency, while pH followed next. In contrast, the hydrogen peroxide concentration had a nearly flat slope, meaning it had minimal impact within the experimental range. This visual trend reinforces the statistical results and confirms the roles of catalyst dosage and pH on the process. The model's R-squared value was 0.6832, indicating that the approximately 68.3% of the variation in the degradation efficiency can be explained by the model. The adjusted R-squared was lower at 0.5155, suggesting that not all model terms contributed meaningfully to predictive accuracy. It's important to highlight that this relatively moderate R-squared might be because we only tested three variables, which is pH, hydrogen peroxide, and the catalyst dosage. Other important factors like reaction time, temperature, and UVC light intensity were not included in this model even though they influence photophantom performance. Despite this, our model had an adequacy precision of 8.78, which exceeds the required minimum of 4, indicating a strong signal. Additionally, the normal plot of residuals showed that the errors followed a normal distribution, supporting the validity of the regression analysis and the reliability of the model within the tested range. Finally, the most optimal conditions identified by the model were solution pH 4.5 and 150 mg per liter hydrogen peroxide with 4.2 gram per liter of catalyst. Under these conditions, the predicted degradation efficiency was 46.41%, which closely matched the highest experimental result of 47.8% in run 24. These results confirm that pH and catalyst dosage had the most positive influence on the degradation process, while hydrogen peroxide showed limited effect within the tested range. The model also indicated that only the linear terms of each parameter were statistically significant, meaning there was no need for interaction or higher order terms. Optimizing each parameter individually was enough to achieve high degradation efficiency. Recommendations for future studies. One of the main areas for future work is testing the reusability and long-term performance of the FECHI-04 at CSBC catalyst. Since this wasn't evaluated in their study, we recommend testing how well the catalyst performs over multiple cycles. This would help determine its practicality and cost-effectiveness for larger scale or industrial applications. We also suggest expanding the parameter ranges, especially for pH and catalyst dosage, to better understand the degradation limits. Our treatment duration was fixed at 30 minutes, which might not have been enough to reach the full degradation potential. Longer treatment times could improve efficiency even further. We also recommend applying this to process to actual industrial wastewater containing multiple contaminants. Real wastewater contains various organic and inorganic compounds that could affect aniline degradation. Finally, conducting a kinetic analysis would allow better prediction of degradation rates and support reactor design. Including other variables like temperature, UV intensity, and mixing rate could also improve the model's accuracy and make it more applicable to real-world conditions. Overall, our study demonstrates that FECHI-04 at CSBC is a promising and sustainable catalyst for degrading aniline in wastewater through the heterogeneous photofenton process. While there's still room to optimize and expand the system, this research provides a strong foundation for developing more effective and practical water treatment solutions in the future. Thank you for listening.